The first part of the fundamental theorem of calculus tells you that the derivative and the integral are inverse operations. So essentially, this said the derivative of the integral of f of t dt is just f of x. And let's give a quick explanation of that. I mean, we explain that about why it makes sense that those two are inverse operations, or like how it makes sense that area and slope are opposites. Let's explain it with an actual example. So we'll come back to this in a second. Let's do an easier example to explain it. Let's let some function f of x equal the integral from like 2 to x of cosine t dt. Right, and we want to find f prime. So according to this theorem, the derivative of the integral, they cancel out, and you're just left with your function. But you see the variable changes. So let's see why that is. If we took this function, that integral is easy enough for us to compute. So f of x is the integral from 2 to x of cosine. Well, cosine integrates to sine. And we plug in our bounds using part 2 of the FTC. We get sine x minus sine 2. So f of x is this integral. Well, that integral just simplifies to sine of x minus sine of 2. And then you want to find f prime. So we differentiate that. Sine of x differentiates to cosine of x. Sine of 2 is a constant, so it goes to 0. So basically, when you do the integral, you do the antiderivative. And then when you differentiate, you just undo the work. So it's like you would do the antiderivative and then differentiate right back. So you end up where you started from, only in between you plugged in your bounds. So pretty much when you find the derivative, when you do the derivative of the integral, you would do the antiderivative, plug in your bounds, and then differentiate. And since you differentiate the antiderivative, you end up right where you started from. But you plug in your bounds. And so over here for our example, we want to find f2 prime. So first we got to find f prime. But to find f prime, if we did it the same way as down here, we would take this function and do the antiderivative, which, by the way, we can't do yet. If we have time this summer, we'll learn a technique called trig substitution. Trig substitution is how you would do this integral, but right now we can't do it. But if we could, you would find the antiderivative, plug your bounds in, and then differentiate right back. And so the derivative, I'm going to do it right here, f prime is just root 1 plus x squared. Right? Because you would anti-differentiate to something, plug x into it, and then you would differentiate right back to this. And then for f2 prime, just the chain rule. So this is 1/2 1 plus x squared to the negative half times 2x, which gives you x over root 1 plus x squared, which is your answer. But the more important truth from this example is that this is really a shortcut. This theorem gives you a shortcut for differentiating integrals. Because the derivative, the antiderivative, their inverse operations, they just cancel out. And this example is probably the best way that I can think to show it. That if you did do the antiderivative and plug your bounds in, it differentiates right back to where you started from. One last example. Let's find f prime, given that f of x is the integral from x cubed to x to the 6th power of t cubed cosine t. Okay, so once again, the technique that we could do if it was an easier expression would be to do the antiderivative and plug your bounds in, and then find the derivative of that function. But we can't integrate that, so we have to use a shortcut. So pretty much the shortcut is that if you were to do this integral, you would find the antiderivative. We'll call the antiderivative capital G of t. And then you would evaluate it from x cubed to x to the sixth, which would be g x to the sixth minus g of x cubed. And then you would find the derivative of that. So g of x to the sixth power goes to 6x to the fifth times g prime x to the sixth. It's the chain rule, why that's there. And then minus 3x squared g prime of x cubed. Because again, g of x cubed differentiates to g prime of x cubed times 3x squared. And what's g prime? Well, g is the antiderivative of this, which means this is g prime. And so we get our answer. G prime of x to the sixth power, you just plug x to the sixth into there. X to the sixth cubed times cosine x to the sixth minus 3x squared times g prime of x cubed. So we plug x cubed into the original expression up here. The key idea behind this is that when you integrate, you find the antiderivative. And then if you want to find the derivative of that, you just go right back to where you started from. But not until you've plugged in your bounds. And then you simplify. 6x to the 23rd power cosine x to the 6th minus 3x to the 11th power cosine of x cubed. The shortcut, I suppose, to doing it this way would be pretty much you plug in x to the 6th into this stuff. So it's x to the 6th cubed cosine x to the 6th. But then since this is our inside function, we multiply by its derivative. And then subtract the lower bound, plug x cubed into there. And then times 3x squared by the chain rule. This is a hard idea to understand. And again, the main thing that you should remember is that the derivative and the antiderivative, they undo each other. So if you anti-differentiate and then you differentiate, you finish where you started from. Okay.